Hi everyone, thank you for coming. So yes, well, first things first, I'm a software engineer, so I do less data science than actual implementing the infrastructure. I have joined the data science and analytics group 2 years ago. And basically we started from 2-3 people, and we're now about 20-25 people. So it's growing a lot in the past 2 years, and it's been an interesting ride so far. What I'm going to show you is to give you a quick introduction of Pirelli. How many of you know Pirelli tires? Yeah, quite a few. Good, but I'll give you a really quick intro of what Pirelli has been doing. And then I'm going to show you the big project that I worked on for the past 18 months or so, Connesso, and I'll give you an overview of the infrastructure, algorithms, models, etc. And then what is, I think, the most relevant thing, at least from my side, is how we reach to the current solution that we have, both from teams and tools point of view, and the lessons learned along the way. So Pirelli is the 5th largest tire manufacturer worldwide. Don't ask me who the first 4 are, because I don't think I know that. I can make an educated guess of who they are, but it's also leader in the prestige and premium markets, which basically means all the expensive tires, all the expensive cars. You can think of Lamborghini, Ferrari, Bentley, McLaren, all the cars. For some of them, Pirelli is the original equipment manufacturer, which makes it very important, basically, to sign one of the brands to kind of have in first original equipment, so that the moment they have to replace the tire, they're highly likely to basically go for the same brand. And this is quite an important point, because when I'm going to talk about the project Connesso, we'll see that we're trying to tackle a market where the original equipment is not the main focus. So basically we want to convince people to replace tires and basically adopt Pirelli where they didn't have Pirelli before. It's also the unique supplier of F1 tires, so that's probably why most people know Pirelli as a brand. It's every time you switch the TV on and you see an F1 race, you'll see Pirelli everywhere. And it has the glam part of the calendar, which also it's quite important for the brand. What happened to Pirelli over the past 2-3 years is a massive paradigm shift from going from being a mainly goods company and becoming a services company. Becoming a services company means becoming more customer-centric, becoming more aware of the end-user needs, but also means widening and broadening the scope of the products and the data related to products with other companies that might benefit from the use of that data. So basically means broadening the value chain of the product they are sold to interact with other companies that might be interested in providing additional services that will eventually benefit the end user, which is a very, very important point. So on this kind of background that started about 2 years ago, Connesso was the first actual product that was going towards that direction of putting the customer at the center of the value proposition. What is Connesso? It's an Internet of Things ecosystem that collects data from sensors that are mounted in the tire grooves. It sends these packets of data from the sensors to a central control unit, which is mounted inside the car. And this is very relevant to the part that I mentioned before, not being original equipment, so not having the possibility to access the data bus of the car itself, but relying on an additional tool that is mounted within the car, so that data is then relied via a mobile application to our cloud infrastructure, and it's then processed to generate the whole data ecosystem that enables providing additional services to the end user. So depending on the data that we have available, we can make some assumptions on providing services. For example, they are geolocated, or they're dependent on the weather conditions, or depending on whether you have a puncture or whether you have some problems with your installations, etc. So it's widening the spectrum of services, but it's also possibly giving information to other companies. For example, you can imagine insurance companies that might be interested in knowing how the drivers are actually using their cars. The current software infrastructure relies on three main mobile applications. You remember that we put a sensor, we installed a sensor in the tire groove. The sensor itself is sending data to a dongle and then sending to the mobile application to the cloud. So the three mobile applications that are involved in this process are a pairing app that basically makes the sensor fitting in the tire groove. The second application is communicating, so pairing the four sensors to the dongle unit installed in the car. And then the third application is the end user application, Connesso itself, that is used by the end user to monitor the current situation of the data coming through the sensors. We also have a bunch of other products. There are byproducts of the main cloud infrastructure. The byproducts are actually giving additional services to customer service, to internal monitoring tools, to basically validate that everything is up and running as expected. Giving this broad set of tools to loads of different personas, loads of different users that are need to access the data, but from different perspectives. The main feature of Connesso is well, not the main feature data related from the data point of view that Connesso provides as a service is the evaluation of the tire wear. So the tire wear is a very, very important aspect of the whole value proposition because it affects three main characteristics of the vehicle, which are aquaplaning, grip, and braking distance. All three are root causes for affected safety. So providing some data packets that can be used to derive information on tyre wear is very crucial and very important for the end user that is actually using the system. In terms of approach to evaluate the tyre wear, there are two families of solutions that we can imagine. One is more related to the physics and the vehicle dynamics. So it's kind of trying to model how the tyre and the vehicle works. So you can imagine how the tyre spins and how it gets worn with time, depending on the weather, on the acceleration, etc. So it's more related to the actual vehicle dynamics. And another family of problems, of solutions, is more purely data-driven. So we kind of abstract from any kind of knowledge of how the vehicle works, and we try to model how the tyre wears, depending on just looking from a broader perspective at the pure data without thinking of the physical model. I'll talk about it in a minute. So the approach of watching the physical properties, it's down to watching or understanding the wear-causing factors. So basically watching the tyre attributes, knowing the tyre attributes, knowing the vehicle dynamics, so the accelerations, weight, all the driving style, so everything related to measurable physical properties of the vehicle itself. The wear-causing factors will then be used to model an expected wear rate, which is then integrated over the distance that the vehicle is actually driven to create a result for the tyre wear, which is, at the end of the day, a number that we estimate and we can compare with some measurable effects of the real car that is going out there. The measurable effect of the tyre wear, the first and most important measurable effect, you remember that the tyre wear was affecting three properties: grip, braking distance, and aquaplaning. Neither of three are actually very measurable in terms of it's hard to go on a track and measure those values. There's one thing that is actually a final end result of reduced or increased tyre wear, which is the rolling radius. The rolling radius is basically a measure of how a worn tyre will cover with a single spin of the wheel in terms of distance on the road. So the physical effect of a worn tyre at the end of the day is a reduced radius, a reduced rolling radius. The reduced rolling radius will then reduce the amount of road that is covered by a single spin of the wheel, which is actually the parameter that we are going to estimate in our data model. So this is the physical model that is actually based on physical observations of the car, so everything that this kind of data coming out of the sensors, angular velocity, patch length, which is the flat part of the tyre that is in contact with the road, So all those physical properties are then used to evaluate the rolling radius and gives then an evaluation of the tire wear. Another approach is to think of the second kind of class of algorithms that we can use is to abstract from the physical properties of the car and try to see at the pure, look at the pure data that are, for example, weather conditions, tire attributes, driving style, telemetry from the sensors, and think of creating a model that evaluates when the tire will need to be changed. So we are not considering anything of the physical thing, of the physical property, of the final spin of the wheel, but we are trying to model just the intervals where the tires will be replaced in a car. So these are basically the two families. What we have done is to build an infrastructure that would accommodate for all the models so that we could have dynamically a model selection of the two families of algorithm and making them run in parallel and making them evaluate what is actually the best performance given from either family. So what we've done, we have created an infrastructure where we have a service orchestration, so our basically backend that runs on AWS. It has a data capture tool or bus that basically receives all the data, which is then orchestrated via through the services that are running in the cloud infrastructure, and these packages are evaluated live as we receive data. We create estimates of the tire wear with both families of algorithms, and we update the data that we store in the cloud to make the best prediction available depending on the data that we have. In terms of architectural choices, this has been very interesting, at least mostly for me, seeing the software engineering part. We started with all sorts of different possibilities. We were building the system from scratch, so we had to consider different aspects of the whole ecosystem, which affected not only the data science part, so not only the basically Python algorithms that we were running to actually do the evaluation, the estimate of the tire wear, but we had also to consider the rest of the ecosystem that we needed to build. The ecosystem means that it's not only backend itself, it means also building the team from scratch. It was like 3 people at the beginning, and we had to scale up and have different tools and different people interacting with all sorts of things. We had to hire people physically to join the team, so we also needed to choose the right technology that could be also scalable in terms of the possibility to hire people that would actually know that technology. So that's why we opted for a Java backend for the main RESTful infrastructure, so that the mobile apps are actually interacting with the RESTful backend running Java Spring, but the data science bit itself is running on a Python container that will we'll run the models in parallel, depending on what we actually need to run. It's all running on AWS, and we tried to be as cloud independent as possible, as we knew that we had then, in the latest maturity of the code base itself, we had to migrate to possibly to different clouds, which is something that is happening now. So in terms of, there's a lot of, at least in the web architecture, there's a lot of buzz around serverless architectures at the moment. I don't know if any of you have used serverless in any sort of form, like Lambda on AWS. Yeah, so you might know that there's a big limitation in Lambda, both Lambda on AWS, both on the size of the package that you create and the execution time. So there's a strict limit of 30 seconds in the execution time, and I can't remember the size, but it's kind of 50 megabytes of code that you can package in a single Lambda function. Shifting towards other possible solutions would be quite complicated, because you write code that runs on a specific infrastructure and you want to actually abstract so that the moment you need to make it run somewhere else, it will run smoothly. In terms of dev team, this is not super interesting. In terms of dev team, we went through a very important learning process of putting together people that were coming from very different backgrounds. So we had vehicle dynamics, who are typically more mathematical, physical background. So they tend to work with MATLAB spreadsheets or hardware. So they're kind of the lower level in terms of software and languages used. Lower level meaning also closer to the physical representation of the data itself. We kind of had a level of abstraction above the data science team that were looking at data from more the modeling and algorithmic part. So working mainly with Python, R, Scala, and all the technologies we're talking about in these days here. We had to run the algorithms on an infrastructure. So we had the digital product development team interacting with the IT department at Pirelli. So you can see it probably as another step above. So putting together the things that the other teams were creating and making them work in the infrastructure, and of course the cyber business unit, which takes care of the actual implementation of their hardware, which is kind of a separated business unit, a completely different world from the rest of the software engineering part. And that probably has proved to be the trickiest work for integrating the various tools in a single ecosystem. We put the algorithms and the models at the center of the whole thing, and doing so, you can kind of see how the flow of the development and the learning process was going. Data science team starting at the beginning with some training data that was provided by Vehicle Dynamics creating the testing data set from indoor testing. So basically everything was prepared in a lab at the very beginning, just even to see if it was feasible as a process or as a final result. So indoor testing data going through physical validation and then feeding this physical validation into the models that were used by the data scientists, feeding back to the cyber unit that were tweaking the algorithms, running on the firmware and on the sensors to tweak parameters for example, the evaluation of the angular velocity. So this data was, particularly at the beginning, feeding back directly into the team doing the hardware to actually physically change things in the parts that they were producing, and then everything composed, putting together and creating the infrastructure that was developed by the digital product development team. In terms of integrating these very different teams, we had to make choices of lots of different things, from version control to using IPython notebooks, from test-driven development, using a shared platform, sharing data across the teams. It was a very interesting challenge to see how the different teams were needed actually to learn from each other how to interact, how to exchange data, how to even package data so that one team could use the data produced by another team, etc. For some of them not even knowing of version control, for example. So some of the team from Vehicle Dynamics never had to open a GitHub repo before, so it was a very thorough and interesting learning process. Lessons learned. Cross-functional team works if we make the clearest and most transparent assumptions on what the tools are, never give anything for granted, sit down together, make things very clear on how to, for example, put a package of data somewhere on S3 rather than use it a GitHub repo. It's never, all the people involved in the process are very smart and very knowledgeable of their specific field, but not necessarily know how to interact with the others. The separation between software and hardware has been painful. I don't think we have a solution there. In terms of practices, unless everything is done under one roof, it's very hard to make the iterations quickly and check that the process, actually the progress of the hardware development. That's because probably in hardware development they come, or at least the people we work with, they come from a more kind of waterfall approach, while we kind of adapted quite quickly to an agile process. So combining the two is always been proved quite hard. So the ideal setting would be to have one product, one team under one roof and working together. In reality, this is very hard to achieve. While for the architectural choices, always try to find a blend of cutting-edge research with very down-to-earth pragmatism and having something that works quickly, that can iterate fast, but can also be modularizable so it can be replaced with something new. Consider vendor lock-in. I mentioned Lambda functions before. Serverless is nice. It's something that everybody tries these days, but you might end up in using something that is not usable somewhere else. We've recently started the migration to the Chinese market, and Chinese market means that we cannot use AWS because there's no Amazon in China. So we need to use Alibaba, and Alibaba has kind of one-to-one match for most of the technologies, but there are a few things that are completely different. For example, we used Connesso for user authentication, and there's no equivalent on the Alibaba cloud for Connesso authentication. So we need to restart writing the authentication part from scratch and try to make it modularizable so that it can be replaced in the code base. Yeah, and with data, start as soon as possible with testing data, whatever is feasible, and try to iterate as quickly as possible, particularly if hardware is involved. We, I don't know if you ever happen to build any kind of hardware. It might be beneficial to start with a very simple proof of concept that could run on a 25-pound Raspberry Pi, for example, and then probably iterate on that model and actually finalize it as a custom FPGA or whatever hardware would be at the very end. And this is pretty much it.
Thank you very much for the very interesting talk. We have now 5 minutes, or 7 actually, for some questions. So I'll go around with a microphone.
Hello. Please can you explain a bit more about what you're measuring and how your field test differed from your lab tests, and also how you're able to get ground truth out in the field, in the real world.
So,
thank you.
Yeah. So the main values that are used to there's data depending on. Okay, so the main values that are coming out of the sensor are pressure, temperature, angular velocity, and patch angle. Patch angle is you can imagine a tire mounted on a car. The first approximation of a tire shape is a circle, but it's actually not a circle because the weight of the tire will make the bottom part in contact with the road almost flat. The patch angle is basically how wide is that flat part in the circle. And the patch angle changes depending on how the tire is worn. So the data coming from out of the sensor are basically these 4 parameters. And on the basis of those values, you can have the approach of modeling the physical representation of the tire. In that case, angular velocity and patch angle are kind of most important. while if you try to abstract and have a more kind of abstraction, data-driven of the whole algorithm, you would be interested in seeing also the variation of pressure, temperature, etc., because they will also affect the driving style, etc. Because we are sending data to a central control unit, the central control unit has an accelerometer that can give information about how the vehicle is manned, and there's actually a GPS there, but the GPS data, as you can imagine, is quite sensitive, so we are using it for indoor testing, mainly to match information on the weather using weather APIs, but never use that for final end clients.
Any more questions?
Hi, going back to the actual physical modeling, you mentioned MATLAB. Why didn't you use, or did you use any CFD and you just fed the data into the code, the CFD data?
Which, sorry?
CFD data.
No. In terms of, so the data that we were using at the very beginning was from a subset of tires that we wanted to address mainly for the specific market that we're going to tackle. For those kind of tires, we initially adopted a quite simple exponential kind of function that would have good results in terms of modeling the tire wear. Exponential as in the real depth of the tire. So that was a good enough solution for the beginning of the implementation of the models. And progressively adding information is still an ongoing process. I don't know if I replied to you.
I think we have time for one more question.
There's one there.
Okay, so after conducting your lab tests to calibrate your sensors, how can you be sure that in the real world on real roads, let's say your measurement of patch angle is accurate? Like, can you ground truth it in the real world anyhow, or how do you do it?
So you can if you limit to the models of tires that you use. So that's kind of a business choice of addressing one market more than the other. So I mentioned that they use the Pirelli is leader in the prestige market. That means that in terms of specific car, it's basically 2-3 cars that are relevant in terms of market, and they're basically the Porsche 911 and those kind of cars. So you can ground truth if you limit to a subset of all the available data, and that's actually when you start widening to a broader range, is when you start receiving some serious noise from all other possible brands and everything. There's no really good solution at the moment, if not having the cars out there and having data coming from different models.
Okay, let's thank Tom again.
Thank you.